Okay, we want to kind of get a little further actually than I usually get in a pre-calculus course, but you're doing so well. We're gonna anticipate that because this is something that really should be covered in the pre-calculus course, the meaning of this E number that you haven't really encountered. But in this course that you will in pre-calculus. And it comes right out of what we've learned to do with compound interest, the way we've learned to understand the which is kind of like, okay, you got this P of T equals P naught times 1 plus R over N raised to the NT. And at this point, I think we understand that this corresponds to breaking interest rate R into N parts and awarding the interest at N regular intervals per year. Okay. So in other words, if N is 4, that means whatever our interest rate is, we're going to divide it by 4 and add that much interest. And we're going to do that 4 times every year. So in 2 years, we do it 14 times. Okay. Or if we compound it monthly, we break our interest rate into 12 parts. Okay. Well, we divide our interest rate by 12 and then do that 12T times in 2 years, 12 times every year for 2 years. So we can actually work this out. Let's say I give you a 10% interest rate, or let's go to 12%. You deserve that, okay? 12% interest rate. If we do that twice a year, then we get 6% 2 times each year. Okay. I'm saying a lot without writing it down because of what we're going to end up writing down. It just to kind of make an impression here. So that means we would multiply by 1.06. 12% divided by 2 is 6%. So we're adding 6% to our principal, okay? Meaning we can multiply by 1.06. When we do that twice, then we get 1.1236. Okay. So we get effectively a little more interest. If we do it 4 times a year, well, 1/4 of 12 is 3, so we'd add 3% 4 times. So to get the amount, just the 1 year equivalent interest, we do 1.03 4 times, meaning we'd multiply by 1.03 to the 4th power. Does that make sense in terms of what we did last time? That'd be just for 1 year. And if we want to do it 12 times a year, we do 1.06. I'm sorry, 1.01 to the 12th. Okay. And we'll come back and do that, but I'm going to get really generous with the interest rate. You certainly deserve it. Okay. So I'm going to declare that for today, at least, we can pretend that you have 100% interest rate. Okay. Now, if you do 100% interest, let's say $1,000. Okay. How much would you have at the end? How many thousand? Well, you get to add 100% of whatever you start with. What's 100% of 1,000? It's 1,000. So you have 1,000, you add 100% of 1,000, you end up with $2,000. Okay. It gets better than that. If you compound it twice a year, then you get 50% after 6 months. So you start with $1,000, 50% of that is $500. You're going to end up with $1,500 after 6 months. Then you get to add 50% of that, which is $750. You'd end up with not just $2,000, you'd end up with $2,250. Okay. Well, that's enough talking about it. Let's write it down. So if you have 100% interest. And $1,000 to start. Then. Well, let's just look at table. Okay. So you would have your principal, which I'll call to you. Then you have your time. We'll just do 0, 1, and 2 years, because at that point we'll be able to easily conjecture what you're going to have after end year. Okay. So we start with $1,000. What's our new amount? It's going to be $1,000 plus 100% of 1,000, right? Well, 100% is just 1. So we have 1,000. I don't have room to write that out. I should have left myself room. Let's just write it over here as a note. A 1,000 plus 100% of 1,000 is 1,000 plus 1 times 1,000, because 100% is just 1, just like 10% is 0.1, 50% would be 0.5, 90% would be 0.9, 100% would be 1. And if we factor 1,000, we get 1,000 times 1.1, which is 1,000 times 2. So our multiplier at 100% interest is going to be 2. So 1,000 times 1.1 is 1,000 times 2. And then our new amount would be $1,000 times 2 times 2, which would be $1,000 times 2 squared. Then our new amount would be 1,000 times 2 squared times 2. After 3 years, we have 1,000 times 2 cubed, and so forth. So after 3 years, we have 1,000 times 2 to the t. Give you a minute to digest that. Okay, in the formula, R would be 1. That's 100% is 1. Okay, and N would be 1 because we're just compounding it annually. And I should have put a heading on this. we compound annually, and that's what this table tells us. And this agrees with what we've got here. If we put substituting one for R and one for M, well, N is here and here, R is here. And that's just E0 times 2 to the T. Again, we let R and both be 1. This is what we get, and that agrees with what the table tells us. Okay, now. Let's compound this twice annually, just for 1 year. Okay, so and I need to have 0 in there. Just in hurry to get to that half here. Okay, we have 0, 1/2, 1. And of course, the table could continue. But what I'm really interested in is what happens to our money just in 1 year. Okay, so P of T is 1,000. Then the new P is going to be a 1,000 times 1 plus 0.5. Now, why 0.5? Because we're adding 50% twice a year. So and that's going to be 1,500. Well, we add 50% again, you get our amount at the end of the year. So that's going to give us 1,500. And, you know, I haven't been writing it out that way, so let me just. Not the way I really want to. This is 50, this is 1,000. Times 1 plus 0.5, of course, that is 1,500. Then our new principal is going to be 1,000 times 1 plus 0.5 times 1 plus 0.5 is 1,000. Plus 1 plus 0.5 squared, or just 1,000 times 1.5 squared. And you can easily work that out. It's $2,250. That compares with what you would have after 1 year at $1,000 at compounding annually, which would be 2,000. Okay. and we want to compare this result to this result, we have $2,250 versus 2,000. Now we can compound 4 times annually. In which case we add %100 over 4, which is 25%. Four times the first year. And not just in the first year, on the right, and beyond, yeah, we do it for, for as long as we maintain the investment. To get the first year amount, well, I'm gonna let you work it out. What would we get? We don't have to do all this. But we don't want to just blindly use a formula. We want to think of what we get if we add 100% over 4 or 25% 4 times 0. Well, I'm going to do this much. Okay. We can understand, I think, perfectly well why that would be. Well, a multiplier for 1 year would be 1 plus 0.25 to the 4th power. Because we're adding 25% 4 times in a year. So take a calculator and calculate that. I can do a binomial expansion, but I'd mess it up. All right, well, at year's end, then we have about $2,440. Now look at the progression. With the number of annual compounding, 1, 2, 4. We have at the end of the first year, we have 2,000. 2,250. About 2,440. I think we can set up another room. But our equivalent interest rate, actually, I want to do the equivalent interest rate. I'm going to leave that alone for a minute, just because I don't have enough room to label. We'll do it more separate. Okay. Okay, so I want you to work this one out. What do we get if we compound that money 12 times? Okay, so we get about $2,600. And I heard the comment, oh, looks like it's going to level off. Okay, so A lot of times you do this and then you say, okay, what if we go to daily compounding? Okay. I want you to guess, since you already observed that it's probably going to level off. I want you to just commit yourself to a guess as to what it's going to be if we compound it daily. Because that's, we're compounding it 30 times as many times per year. Okay, now you didn't want to guess. Yeah, I'm not sure, and then you guessed, say probably another 100. So you guessed 2,700, right? And if you plug this in, you found that you get 2,713, which means that was a great intuition. Okay, and that was very good because what you did was you saw it was going to level off. And you actually have pretty good intuition about how much it was going to level off, although 100's a pretty easy guess to make. It was an excellent guess, okay? Now, I'm not going to push you to make another guess. Since you're on a roll, I don't want to ruin that, okay? Let's do it. A million times. Okay. And after that, we'll look at what the limit is. Okay, I haven't looked at your result. Haven't allowed you to tell me. The approximate limit of this whole process would be about this. Okay. Fairly easy number to remember because all that repetition. And you might think that it keeps repeating the 1828, but no, it probably won't repeat that 1828 for about another, let's see. Another 100 feet. Okay. Expect to go maybe another 100 feet. Writing it out like this before you get another 1828. And that's just random. It could occur earlier, could occur later. That's kind of what it's said. Okay. Now, what you probably got was very close to this. You probably got 2718. You might even gotten the 28, did you? Did you get the 18? Probably not. You got the 28 though. Yeah, okay, that's kind of what I expected. Okay, 0.18 what came after the 8? 0. And that 0 might round up to 1. It might not, but we're not going to worry about that. Okay. So 1,000,000 times you got it down to the penny. Now these were approximate, they were within $1 or $2 or $3. Okay, so that's kind of interesting. And then the exact limit. Well, I don't have 100 feet to write this out. And even if I did, I wouldn't even be off to a good start because it goes infinitely far and there's no pattern. Okay. There's no pattern to this. It's an irrational number. You learn about rational and irrational numbers. I would assume since you seem to have a pretty good excellent background for this course. Okay. Which is why we're going way beyond the course that we're in. And I'll repeat, you're doing this voluntarily, right? Okay. You're doing it because you like it, you're interested. That's wonderful. Okay. Exact limit is 1000 E. Okay. Well, let's see if we can define this number E. It's easy to calculate to any number of decimal places. When I say easy, I didn't mean quick. Okay. Yeah, I didn't mean it wouldn't be error prone. You let a computer do this and make sure your computer doesn't have a bunch of base 2 errors in it. Well, computers haven't had that problem lately. Okay. So. It's P naught times 1 plus 1 over n to the n, right? Okay, well, digest that and make sure you understand why that's true. Oh, heck. I didn't record any of that. Oh, darn. Well, where did I leave off? I want to summarize this because it's really kind of important. Okay, so I'm pretty sure. I'm not sure. I know we recorded where you guessed 2,700, 360 compoundings, we got this. Then you did for 1,000,000 compoundings. Okay. And I guessed that you get something that was accurate. Well, okay. I guessed you would get about 2.718 or 2,718.18. And I added that 0 because that is the next decimal place that you got. Okay. Now, you understood that there's a leveling off, a limit. And I wrote out the limit, which is very, very close to what you got for 1,000,000 compoundings, 2,718.281828. And I said, okay, well, the exact limit could be 1,000 times E. I noted that your 1,000,000 compoundings agreed with this approximate limit, and I commented this approximate limit looks like you've got a repetition 1828, 1828. It's an irrational number. That 1828 doesn't repeat again for a while. Okay. And I estimated that it would occur if I keep writing this out, maybe another one about 100 feet down, maybe every 100 feet or so you get one. Okay. It'd be, about one every 2,000 numbers. If I get 2,000 numbers into 100 feet, actually it'd be a few hundred feet because those numbers aren't that close together. Okay, so, and we understand, you understand irrational numbers versus rational. This is an irrational number. And I commented that most of the students who get for calculus these days, it's COVID and everything, don't understand that distinction very well. It's kind of an important distinction. Okay, so then I commented the exact limit is 1,000 E. Where E is arguably the most important number in mathematics. People think maybe pi is really important, and it is, but you can define pi if you know what E is and know how to use complex numbers. And you don't, but just giving a quick synopsis of what E is, if not the most important number, one of the 2 or 3 most important numbers. I still think it's probably at the top. What do I know? Okay. Then we observe this in order to explain say that the 1 year amount at 1,000% interest compounded n times is what? Well, exactly what you've been doing. It was 1,000 times 1 plus 1 over n raised to the nth power. So you're doing that on your calculator, and you have no, to do a million of these compoundings, you'd probably go for a year or two without making a mistake. At some point, you'd probably make a mistake and get wrong, actually, if you're doing it by hand. Okay, and no, nobody's going to go a year or two without making a mistake. So our multiplier for 1 year is just this 1 plus 1 over n to the n. So whatever your initial principal is, that's what you multiply by. Now let's take the information we have and make a table for the values of 1 plus 1 over n to the n. Okay. Well, we've worked it out for n equals 1, 2, 4, 12, 360, and a million. So right there are those numbers. And the multiplier is just, well, we multiplied by 1,000 to get these numbers. So our multiplier is just 2 in this case, 2 times 1,000, 2.25 times 1,000, and so forth. So here are our multipliers. Okay, you see that by the time we get to 360 compoundings, we're up to 2.713, which is pretty close to 2.718. The million compounded, we actually do get 2.71828, but then we get a 0. The approximate limit is this. So I didn't write the approximate limit, but the exact limit is what I'm going to say, and here's the expression I'm really getting at. It's the limit as n goes to infinity, because what's n doing here? Started with 1, went to 2, went to 4, went to 12, went to 360. Those are all numbers that we understand pretty well. We went to a million, that's harder to understand because it's so big. So at this point, we're beyond numbers we understand, but the numbers get bigger. You can't have a million billions or a million billions of million billions. It gets, no, there's no limit to how big numbers get, but in the limit, we do get E, and nobody can write it out. Okay. That's the definition of E, and that should be done. And in some places, I think it is standard thing that you learn in pre-calculus. So you're prepared to use it and understand it to some extent when you use it in pre-calculus. And because we do use it, and then understand it, and understand a little bit about limits, so that when you start talking about limits in a calculus course, you have some inkling of what a limit is intuitively. Okay. Another thing I'll write down a formula for calculating E. Okay. First, we're going to write out the formula for E to the x. Pattern. You see the pattern. You have an x squared, x cubed, x to the fourth, x to the fifth, x to the sixth. What's going to be next? It'll be x to the seventh, right? And for x squared, we got to divide by 2. For x cubed, we divide by 3 times 2. For x to the fourth, it's 4 times 3 times 2. And of course, times 1. And we can actually write the times 1 here. This x could even be x over 1. Okay. I started writing the 1. I better continue it. And then x to the fifth over 5 times 4 times 3 times 2 times 1. The 1 is kind of redundant, but we do tend to write it out. And then I got tired of writing all those numbers. So instead of 6 times 5 times 4 times 3 times 2 times 1, I wrote 6 with an exclamation point. That means 6 factorial. It means 6 times 5 times 4 times 3 times 2 times 1. And at this point, it should be totally obvious how this continues, and it continues forever. These numbers that you add get smaller and smaller. Okay, like 1 plus x. Okay, let's say x equals 1. You want to get e? You just do e to the 1. You let x equal 1. Okay, 1 plus 1 is 2. Okay. 1 plus 1 plus 1 squared over 2. Well, that's 2.5. Okay. Yeah. Okay. And x cubed over 3 times 2 times 1 is 1/6. You know, 1 over 3 times 2 times 1 is 6. And that gets us up to like 2.66 and 67. Okay. And then this number is getting kind of small. It's less than 0.01 because 4 times 3 times 2, no, sorry, it's 0.04. That gets us up to about 2.7 if you work it out. This is less than 0.01, and so forth. So if you keep adding these numbers, you keep the levels off, you keep adding tinier and tinier numbers. Eventually, you get all these decimal places. Okay. And there's much more I could say about that. So if we replace x by 1, we get a formula for e. And it's something we can calculate. It's just that the calculations would get really, really long. Okay, so okay. And that is just P naught e to the RT. And you would have used e to the RT in your semi-mathematical and apparently pretty good finance class, okay? Yeah, it was taught to a broad spectrum of students, so they couldn't get very rigorous with it. And if they had, you know, you might have even gotten overwhelmed at that point, okay? They had really, so, and like I said, finance is highly mathematical. And this is, you know, I wouldn't call this highly mathematical, but it's still you know, kind of starting to get there. Okay. Um. Okay, so there it is. You just do P naught E to the RT. So for 1 year, you do P naught E to the 1T or to the R. And if R is 100%, that's just P naught E to the 1, which is P naught times E. And that's what we actually calculated over here. P naught was $1,000. P naught times E is approximately this. It's equal to 1,000 E. And that comes right out of it. Again, if R is 1, meaning 100% interest, and N is 1. I'm sorry, R is 1 and T is 1. And you get P naught times E. Well, and then if you go multiple years or fractions of a year, just plug in how many years or T, and you get your result. Okay. One quick connection. The basic toolkit exponential function is y equals 2 to the t. Remember that? Because we did that some time ago, and we'd be pretty good at that. Okay. That's how it works. Y equals e to the t. Well, e is between 2 and 3. Okay. So y equals 3 to the t would actually start lower over here on the left, but then it would go up higher. So y equals 3 to the t just gets steeper than y equals 2 to the t, and I didn't draw that quite. It got a little too steep to get there. And you know, you could make a table for 3 to the t, and you know, just from t equals -2 to 2, and get that shape. Okay. If you wanted to do an approximation of y equals e to the t, you could just use 2.7. Okay, well, 2.7 is between 2 and 3, so e to the t is between 2 to the t and 3 to the t. So it's not difficult to understand that graph, and it's not difficult to visualize how your investment or population or whatever it is you're modeling, it could be guppies in the tank. Okay. It's not difficult to visualize that growth. If we do 2 to the t, you can visualize 2 to the t, you can visualize e to the t. Okay. All right. Just rescale your x-axis is another way to do that. Yeah, we'll talk about that. We've only got 2 more classes after this one, so we'll see how far we go and how far you want to go. Okay, so now that's a little aside, just so you can connect this with your graphs and what you know about graphs I wanted to mention. Now we want to come back to this limit and ask why this is. Okay, I say that it is. We know what the limit of 1 plus 1 over n to the n is. That's e. Okay. Well, I'm going to take use a mathematical script. Okay. And let me stop and think about this to make sure I don't write it down wrong. We get everything backwards and upside down lately when I don't stop and think. So I wanted to stop and think so I don't cause confusion right here. So if m equals R times M. Okay. Wait a minute, I got it wrong. Okay. I stopped and thought about it and still got it wrong. Okay. Let's make sure I really got it wrong. I think I would. Okay, if n equals mr, then what's r over n equal? Well, I'm gonna let you write that out. Write that out and tell me how that simplifies. Okay, what I'm using is I'm how to use what's called a change of variables. It's a mathematical trick. Not one you're going to encounter much in pre-calculus, maybe a little bit, and in calculus, you, especially to get into integral calculus, it becomes something you do a lot of. Okay, but we'll see one day. Okay, different context and change of the variable. So if n equals mr, then r over n is just r divided by mr, right? Now, you're probably taught you can cancel out the r and put a 1 up there, and that's true. But I'm going to write it out as it really is. About any tricks. Okay, I could write this fraction as this because the numerator is still r. If I multiply 1 by r, I get r. The denominator is still m times r. R over n equals 1 over m. Now, if n goes to infinity, that means n can get as big as it likes. Then m will go to infinity. M won't be as big as m, and if r is reasonable interest rate, because r would be less than 1, but still, n can get as big as you like. So no matter how small r is, m can still get as big as you like. Okay? So we say if n goes to infinity, then m goes to infinity. Also, what is nt going to equal? Well, if n equals mr, nt equals mrt. So the limit is n goes to infinity of 1 plus r over n to the mt equals the limit is m goes to infinity of this expression where we replace N with MR. This expression just becomes 1 over N, the R over N becomes 1 over M. So and N is MR. So I simply replace all of my N's in this expression with MRs, and I've simplified the R over MR. This would give me 1 over L. Okay. Now, the limit is M goes to infinity. At 1 plus 1 over M raised to the MRT by the laws of exponents. Its limit is M goes to infinity of 1 plus 1 over M raised to the M raised to the RT. Okay. And that's by your rules for exponents. A power of a power, you multiply powers. So I can sort of factor this MRT, but it's not really factoring in the standard sense. But I can use the rule for exponents to write the MRT exponent as M to the RT. What will the quantity raised to the M to the RT? Okay, any rules for exponents tell you that this raised to this is this raised to this. So there's no change. Okay, well, we're done. Because what's the limit of 1 plus 1 over M to the M? As M goes to infinity. It's E. Because it doesn't matter if I use M, N as my variable, okay? Doesn't, you know, we generally use N in the definition of the in the definition B. Okay, we could have used M just as well. We could have used aardvark for our instead of N, although nobody would do that. Okay. We used M. Well, there we have E to the RT. Now the algebra is a little challenging in doing this. Okay. It's worth stretching yourself a little bit. If you take stretching, I think you're understanding every step. Probably going to need to ponder a little bit if you want to understand the whole process. But each step in the process is very simple. Okay. Now, how would we think of letting M equal MR? Well, it's because I want to get a 1 plus 1 over M to the M. Okay, so, you know, you wouldn't necessarily think of that, although, you know, with a little more mathematics behind you, I think you might. All right, well, anyhow. We've shown that the limit as N goes to infinity, 1 plus R over N to the NT is E to the RT. And there you have reason that continuous compounding magically makes this thing morph into this. Okay. That's challenging. At the pre-calculus level, that's a pretty challenging argument. And since this is only intermediate algebra course, which is a prerequisite for pre-calculus, you're pretty deep into pre-calculus, even having the interest to want to look at this argument, okay? Now, if you'd have known what was coming, you might not have wanted to look at it, but I know you would have. Okay. Well, kind of remind me that we want to get into the bell-shaped curve. And just to give you a little teaser. And we're over time, so quickly. The bell-shaped curve is essentially just a graph of y equals e to the negative x squared over 2. And that's a basis for a whole lot of statistics. And since you might well, you're already fascinated by some aspects of biological statistics, which is in biology being your intended major, you might find it interesting. Since you're not going to be tested over it, you'll find it twice as interesting.